every religion we know of has an origin story about how the cosmos, how the universe came to be, and how the people came to be in it. We're familiar with the one from Genesis, but of course there are hundreds, thousands of others, every culture. Modern day science, especially astronomy and physics, asks us to believe probably the weirdest story of all, which is that we live in a cosmos that is not just inconceivably vast and inconceivably old, but it's getting bigger by the second. It is expanding. And furthermore, it's expanding because 13.8 billion years ago, it burst into existence in this inconceivable explosion we call the Big Bang. That originally started out as a derogatory term, by the way, but it's been embraced by the community. And the question I ended up asking when I was writing this was, how did they even know all that? I mean, did the astronomers and the physicists sit around one day and just make it all up? No. In fact, when you start digging into the history, and this is what I found so fascinating, they had to be dragged kicking and screaming to this conclusion that it wasn't natural, it wasn't obvious, even to them. They were forced to it by getting hit in the face, to mix a metaphor, by data that they couldn't avoid. And that's what I'm going to describe today, how that happened. And most of the action, as we'll see, really started almost exactly a century ago, in the 1910s and 1920s. But first, I'm going to set the background, set the scene here. Now, as many of you may know, what we now call the scientific revolution started in 1543, when a Polish astronomer named Nicholas Copernicus, that's his Latinized name, on his deathbed, no fool he, published a book, the Latin title is Revolution of the Heavenly Spheres. And he postulated that the motions of the planets across the sky made a heck of a lot more sense if the sun was in the middle and everything, including the Earth, went around the sun. Well, the moon went around the Earth, but everything else was around the sun. That was a profound idea, but the really profound implication of that, which was very obvious immediately, was that the planets, these lights we see moving across the sky, you have Mars, Jupiter, Venus, and so forth. The planets are other worlds, and the stars are other suns, just like ours. And in 1610, the Italian scientist Galileo, we'll come back to him in a second, he published a little pamphlet, Sidereus Nuncius, which is invariably translated the Starry Messenger, in which he described what he had seen through a telescope that he had made himself. He didn't invent the telescope, but he was the first to turn it to the heavens. And what he saw were mountains on the moon. Venus became not a bright dot in the sky, but a disk. Actually, it had phases like the moon, which Copernicus could have predicted. The planet Jupiter had moons going around it. We call them the Galilean satellites today. These were literally other worlds. Saturn had these weird ears. He couldn't figure out they were rings, but anyway. Then there was another big idea that came out of this revolution. Actually, you can trace it back to the ancient Greeks, but Galileo, the German astronomer Johannes Kepler, the Danish astronomer Tycho Brahe, all about the same time, towards the end of the 1500s, early 1600s, we're coming to this idea that the heavens and the earth are one, and they obey natural law. Now, before that, it was assumed that the heavens are some ethereal substance that was different than anything here on earth. Quintessence. Their whole philosophy is built on that, but they were grappling towards this, and the flesh really got put on that by Sir Isaac Newton towards the end of the century, when he published his laws of motion and laws of gravity, which put mathematical form to that. But the real implication was that the same force of gravity that holds the moon in its orbit around the earth and the planets in their orbits around the sun is the same force of gravity that will pull anything to drop to the floor. The heavens and the earth are one, and natural law, same rules everywhere in the universe. That just blew people's minds. And then, not only is the universe very large, and that was an implication of Copernicus, because if Mars is another world like our own, and all we see is a little dot in the sky, it's got to be really far away. Ditto for Jupiter and all the others. So they knew it was large, but towards the end of the 1700s, amateur, we call them geologists now, natural philosophers, started looking at these features they saw, these strange striations and things they saw in cliffs, and they were starting to do road cuts in those days. And realized that these looked exactly like the features we could see being, the sand dunes we saw being formed today, or the mud flats, so forth. But when they calculated how long it would take to wear down a mountain by the erosion we can see going on, or how long it would take to build up the layer after layer after layer of sandstone that they could see, they came out with answers like millions of years. The earth was incredibly old, a lot older than the Bible seemed to imply. And today we're actually going to talk about a fourth big idea, which is that the universe grew from a very different beginning, which actually isn't implied by any of the others. But let's go back. Along about the end of the 18th century, 19th century, new instruments and new technology really started to allow people to put some hard numbers and precision on this. And we're going to start actually a little bit earlier than that. The Milky Way. If you've ever been into a dark sky or up in the mountains on a clear night, you can see this faint band of light. This is a modern photograph, time exposure. But with your naked eye, you can see this faint band of light going across the heavens. I'm sure people have seen that. What is it? Well, the comparison to milk is at least as old as the ancient Greeks, whose word for milky, by the way, is galaxius. That word was anglicized to galaxy by one Geoffrey Chaucer in 1385, who also coined the term Milky Way. But in 1610, when our boy Galileo was looking, here we go. In 1610, when Galileo was looking at, sorry, this is my wife's computer, so I'm not, looking at the telescope, this telescope, what he saw was that this faint wash of light resolved into zillions of stars, lots of very faint stars. So, okay, this was not just light, it was something else. But what? Now, as early as the 1750s, there were some speculations that the Milky Way was a gigantic disk seen edge on. You can imagine this. Now hold out your hand like this, and imagine that you have a disk that's the palm of your hand, and then rotate the palm of your hand so you're looking at it edge on. You get a band, it's thin. right? And so that's a disk, and we're embedded in it, and we're looking at it edge on. That's what you would see. Most famously, many of you probably have heard this, the philosopher Immanuel Kant, he was a German philosopher, in 1755, said, well, you know, the astronomers are finding all these fuzzy patches of light around the sky. They called them nebula, the Latin word for cloud. And not just this, but just all over the sky. And you'd see these fuzzy things, and you know, they couldn't make out what they were, but they knew they weren't comets because they didn't move. But in any case, Kant suggested that these were other, he called them island universes, other disks of stars that were like our own. He couldn't prove it. I mean, he was a philosopher, not a scientist. But in 1785, the German-English scientist William Herschel and his sister Caroline, she was his, quote, assistant. I mean, she did a lot of the observations too. They had a big telescope in their backyard in London. Those were in the days when there were still dark skies in London. And they decided to get a sense of what this disk they lived in looked like. And so they tried mapping it out. They assumed that the fainter stars were further away, and they just looked all over the sky and counted stars in each direction. And they got, this is a modern rendering of what they saw. They had a diagram much like this in their paper. But they estimated that it was this sort of flattened thing. And as far as they could tell, the sun was pretty much in the center. Let's see. Sorry. This is what happens when you use somebody else's computer. Okay, but they couldn't tell actually how far away those stars were. In fact, it wasn't until 1838 that a German astronomer named Friedrich Bessel. How many of you have taken math? You know what Bessel functions? Well, that was him too. Anyway, he actually managed to do it. He managed to look at a star and tell how far away it was. And the way he did it was by applying this ancient method called parallax. And we can all demonstrate parallax like this. Just hold up your finger. Okay, you can either alternately close and open each eye or move your head. And you can see, when you look at the far wall, your finger seems to bounce back and forth when you do that, all right? That's parallax. Well, the Greeks knew about this perfectly well, thousands of years ago. And they used it, methods based on parallax, to get a pretty good idea of how far away the moon was. You look at it at different points on the Earth, and they could figure that out. And it's about 250,000 miles. By the 18th century, astronomers had used those methods to figure out the distances to pretty much everything in the solar system. The transit of Venus comes into this, which is another story we're going to ask about in Q&A. But it's basically using the same method. It's the same method that surveyors use here on Earth to figure out how far away things are. Now, in principle, you could have used this to figure out how far away the stars were, because, people try to, as soon as Copernicus published, astronomers were trying to do this. First with naked eye, then with telescopes. And the idea is, if you look at a star, a bit of a star field through your telescope, when the Earth is right here in its orbit, then you wait 6 months and look at it from here, And a nearby star, relative to the distant stars, would seem to be in slightly different positions. Here it is one time, there it is 6 months later. In principle, you could do that. And people tried for centuries, and nothing moved. Yeah. So the only answer they could come up with is stars are just ridiculously far away. And they sort of are. But Bessel finally did it using exactly this method in 1838 with a then state-of-the-art telescope. And we still had dark skies in those days. And he was looking at a star. It's called 61 Cygni. The name doesn't matter. But he measured an angle. I worked it out. If you imagine somebody standing down in Belhaven Park, south of Alexandria, holding up a quarter, and you were trying to see that quarter, here it's 10 miles. That's the angle he measured. It's just a tiny infinitesimal fraction. It looked like a small crater on the moon or something. It was just ridiculously small. And from that, and by that point they knew the distance from the sun to the Earth, so they could work out, that baseline. It's 186 million miles. He got the distance to this star, 61 Cygni. And he got about a distance that it would take so far that it would take light over 10 years to traverse the distance. And he didn't call it light years, but that's what it was. That's pretty good because the modern figure is just a little over 11 light years. But it was this ridiculously small angle, and he did it for several other stars. In fact, as the 19th century went on, they got more, astronomers were able to get more and more stars, and they were able to see they could get distances out to about 100 light years. Now, that was a lot of stars. That's 60,000 stars in that volume. Even though they're like 4 light years apart on average. But they couldn't get distances beyond that. And that's important because we're going to come back to it. Meanwhile, though, in the 19th century, there was coming up with some other mysteries that the ancients had not known about. Remember those fuzzy patches of light and nebula that were all over the sky? Well, all they could do was look at it with their eye. They didn't have photographs. But photographs, recognized in modern photographs, date back to about the 1830s, the first experiments, daguerreotypes, things like that. And immediately, gentlemen astronomers, amateur astronomers, started trying to adapt it to astronomy, and they got nothing. I mean, it was really hard for a bunch of reasons we don't need to go into. But it was just very, very difficult to do it, and it took all the way to the 1880s. And the first really decent astronomical photograph is that. It was taken in 1882. It shows a nebula, a famous nebula. It's the Orion Nebula. You may have seen it on a dark sky. It's a fuzzy patch on Orion's sword. Below the famous 3 stars. But of course, what he saw, you see a fuzzy blob with your eye, and you take a time exposure, and you get a bigger fuzzy blob. We know now it's gas and dust, and it's where stars have formed. Really interesting by itself. But they started taking other things. I mean, okay, this, if you can see it, this was the first 1888. The first decent photograph, real photograph of the Andromeda Nebula. Now this is in the constellation of Andromeda, the summer sky. And you can actually see the Andromeda Nebula with your naked eye, barely. On a really dark night, you see a fuzzy thing. I've seen it on a really dark night. It's really cool, I don't know what it is. But what you actually see with your naked eye is this bright blob here at the touch. When you take a time exposure, which is what that is, you see this extended structure, and it's a little hard to see because it's a spiral centered on the blob, but at an angle. Okay, but you can see faintly spiral arms there. That was weird. Oh, by the way, that thing is huge. If you could actually see that whole thing with your naked eye, it'd be 6 times bigger than the moon. You would really notice it if you could see it. But then they took other nebula, and you could see spiral shapes. That was about 1899, I believe. And this one, 1910. You see these spirals. What are they? Yeah, what are these things? This became a big debate in the field. Were they other island universes, like Kant has suggested? Were they gas clouds that were nearby? It was such an argument that right here down at the National Museum, Smithsonian Museum of Natural History, which was new at the time, it was built in 1910, the Smithsonian Institution held what they called a great debate. With 2 eminent astronomers arguing the 2 sides of this question. And on one side was Harlow Shapley. At the time he was 35, a little bit younger than this picture. And he's a major figure in this field who deserves to be remembered. His granddaughter, Deborah Shapley, lives right here in DC, and would be happy to talk for hours about her opinion. But not only had he made major discoveries in astronomy, even by this time, and we'll come back to that. But shortly after the debate, in 21, he was named head of the Harvard College Observatory. He did a lot to promote women in astronomy, bring women into astronomy against considerable opposition, I might add. He later stood up to Joe McCarthy, became a political activist during the New Deal, and was a science popularizer. It was quite good. But in the great debate, he took the position that these things had to be nearby gas clouds. Now, why did he say that? Well, he was basically led to it by his own discoveries, which rested on, remember I was talking about the astrophotography, the photographs? Okay, the way they actually did it, the astronomers actually did it, is they didn't use plastic film. That actually didn't come along too much later. They had these glass plates, the same kind of thing that Matthew Brady used. And they took negatives. They usually work with the negatives because printing it, adds errors. But this is an example of one. It shows a structure called a large pendant cloud. Now these plates were about big. And by the early 1900s, the Harvard College Observatory, in particular, it was one of the leading places in the world, had accumulated thousands of them. And it kept coming out. And every one of them, remember they had no automatic scanners in the days, every one of them had to be scanned by somebody who really knew what they were looking at, really knew what they were doing, highly educated, with a magnifying glass. And mapped out by hand and calibrated, and all those stars, all that stuff, all had to be done. So in order to do this, the then head of the observatory, his name was Pickering, William Pickering. He hired a bunch of very talented women, college graduates for the most part, who couldn't get jobs even remotely equivalent, suitable for their talents, not in those days. This actually started in the late 19th century. Their story is recounted in a wonderful book, Glass Universe. Over here you see a photograph of them in their workroom. This is pretty clearly staged, by the way, posed. But it does give you an idea of what was going on. The lady in front, the older lady, is Annie Cannon. She was sort of the matriarch of the group, this sort of bright, bubbly personality. The tall woman standing right behind her is Williamina Fleming. Fleming was a Scottish immigrant whose husband had abandoned her, left her with a small child. So she been forced to go to work as a maid for William Pickering. And Pickering's wife quickly convinced him that their maid was a lot more talented than cleaning house. So he hired her, and there she is. Now all of these women made, because of their meticulously compiling all that data, we call it big data analysis now, they all ended up making major contributions to astronomy. And we could talk about them for hours, but I want to look at the retiring and partially deaf Radcliffe graduate in the back with the magnifying glass. Her name was Henrietta Swan Levitt. I looked it up, it's Levitt, not Leavitt. And here's one of the plates she worked on with her notations. Again, it shows the small Magellanic Cloud. It's a patch. The Magellanic Clouds are in the southern hemisphere. They were discovered by the Jones expedition, and they look like little patches of the Milky Way that have gotten detached and floated off somewhere. They're groups of stars, and she was looking at that. And in particular, she was looking at variable stars. Now, variable stars are, they ebb and flow in brightness. And there are lots of them. They're all over, most stars, in fact, are variable to some degree. They're all over the sky. Here's, if you don't mind a plot. Here is, shows one type. They're called Cepheid variables, and they'll be important. Ebbing and flowing. If the brightness goes up, it comes down. About 4 days later, up and down, up and down. And it's a very characteristic sharp peaked curve. The important part here about Cepheids is that if you look at one Cepheid, the spacing of those peaks might be 5 days, as it is here, and another it might be 1 day, another it might be a month or so. The spacing varied. Levitt looked at all that, and in 1908, she was 4 years old. She published a paper in the Harvard College newsletter, which was widely read, by the way. Looking at nearly 2,000 variables in the two large and small Magellanic Clouds. I'm surprised she wasn't blind as well as deaf after doing all that. But she noticed something striking about them. And I don't know if you can read this, but here is a sentence she puts in. This is the published paper. It is worthy of notice that in Table 6, where she lists them, the brighter variables have the longer period. Okay, remember that. 4 years later, Levitt published another paper looking very carefully at 25 variable stars. They're all Cepheid variables, by the way, and the small Magellanic Cloud. This is just one location. And in that paper, she repeats the longer periods, brighter and adds this sentence. Since the variables are probably at nearly the same distance from Earth, their periods are apparently associated with their actual emission of light. Now, what does that mean? Those are her graphs. This is a modern version. Ignore the part where there are things down at the bottom. But what you can see is there's a very tight correlation. Now, the problem in astronomy, in finding distances of stars, is all you see is a point of light. You don't know if it's a bright thing that's far away or a dim thing that's close. You have no way of telling. Unless you can do parallax, but beyond parallax you can't. What she was saying was that the period correlated very sharply. You can see it right here, almost perfectly with the brightness. So you could time the period. All you had to do was look at the thing. You didn't have to know how far away it is. But if you could time the period, you'd know how bright it actually was. And you know it, you know if it was a bright thing or a dim thing. And by looking at how bright or dim it is in your telescope and comparing it to how bright it actually was, you can work out the distance. That's an inverse square law with the math. But in any case, with that sentence, with that observation, with that insight, Henrietta Leavitt essentially cracked open the universe, because now Cepheids are really, really bright. I don't know if you can see the axis there, but they can be 10,000 times more luminous than the sun. You could see these things for immense distances, way beyond anything you could do with parallax. So suddenly, people could look out and just measure distances. If you could find Cepheids inside any object, you measure distances just way beyond anything possible with parallax. And one of the first astronomers to jump on this was our boy Harlow. He started looking at globular clusters, which you've all seen pictures of these. These are, again, these things are all over the sky. They're these beautiful jewel box clusters of stars. They're held together by gravity. They're clearly made of stars. This is a modern photograph, I think, by the Hubble telescope. But he looked for Cepheids in these things. And he found them. And so each globular cluster, he could not only tell where it is on the sky, but he could tell how far away it was. And that allowed him to make a 3D map. And here it is. This is a modern redrawing of it. The sketch made by the Herschels is this black thing right here. That's the position of the sun. And that's where Shapley found all the globular clusters. Now, it's a little unclear where this distribution does. This is the plane of the Milky Way, by the way. It's a little unclear where the center of this distribution is. I mean, it's skewed, but it's clearly not centered on the sun. He estimated that it was the center of this. It's actually 3D, not just 2D. Was roughly about right there, which at a point that lies in the direction of the constellation Sagittarius, which is in the summer sky. And he estimated the distance to be 60,000 light years, which that's actually an overestimate. It's 26,000, but okay. Given what he was doing, either way, that's just immense. I mean, this Milky Way structure, this disk of stars, was just huge beyond belief. And that's what persuaded Shapley that these spiral nebula had to be nearby, because if they were other structures this big and they looked that small in the sky, they'd have to be millions of light years away. It's just ridiculous. And to believe something like that, you'd have to have really strong evidence, and which didn't exist. So that was his view, and that was the majority view among astronomers. Pretty much everybody believed that these things were, well, not everybody, but a lot of astronomers, the majority of astronomers believed that the spiral nebula were nearby. Maybe there were solar systems in the process of formation, who knows? But there was that other side of the thing, and that was taken up by another eminent astronomer, Everett Curtis, who argued that the Kant perspective, these other spirals are other island universes, and that was the phrase that was used. And I mean, part of his argument was that you know the Milky Way is a disk. Those things are disks. Why not? Seems plausible. But another argument rested on another recent rush of observations, which, and here's a little background. Even the ancients knew that a sliver of glass or a mirror or something could break light into this pretty colored pattern. We've all seen that. First person to call this a spectrum was Isaac Newton, who studied the phenomenon in the 1600s. Spectrum, by the way, is Latin for ghost or after image, and it's the origin of another word for ghost. It's called spectrum. Same word. But the real advance came in the early 1800s, mustachioed-looking young gentleman, and he was young, he was in his mid-20s. His name was Joseph von Fraunhofer. I can remember my college Sherman. And he invented this device called a spectroscope, where basically he had a little slit to let the light through, and then he did the prism at an angle so that the spectrum was spread out that way, relative to the slit. So we could analyze all the colors. And here he is demonstrating it to a bunch of impressed gentlemen of leisure. When he looked at the sun, he saw that. This is a West German stamp issued back in the 80s to honor this discovery. What he saw when he looked at the sun was that there were wavelengths missing. Now, because of the way the spectroscope worked, these showed up as lines, and to this day, those are called spectral lines. And it was this remarkable pattern. He looked at bright stars like Sirius in the winter sky, and a few others, and he saw similar but different patterns. Among other things, it told him those lines weren't being caused by the atmosphere, because the atmosphere would make them all the same. He didn't have a clue what any of that meant. And sadly, he never found out, because he managed to give himself, his glass making managed to poison him with heavy metals, and he died at age 39. It's too bad, he was a genius. But in the 1860s, German chemists managed to figure it out. It is discovered if you take pure elements like sodium, hydrogen, calcium, mercury, and you heat it up in a flame, say. And one of the scientists who were doing this heated this stuff up with a burner of his own invention. His name was Bunsen. If you remember that. But he invented it to do these experiments. But anyway, you heat up elements and you see through the spectroscope that they emit these very precise wavelengths, these lines, they're still called spectral hertz, in a specific pattern. But if you put them in front of a bright light, like the sun, those bright lights turn into dark lights because they're absorbing the light. But exactly the same wavelengths. And so you could look at these wavelengths and look at the sun, which is up here, and identify which elements were making which one. Now, in the words of our president, this was a big effing deal. For astronomy, because it meant you could look at anything in the sky. If you could get a spectrum of it, you could tell what it was made of. And by the way, what you found in the sky was always exactly the same elements you saw on Earth. Again, the heavens and the Earth are one. It's the same stuff. But now there's data. You've got it. You know that. And to say that's a big effing deal, but we're going to look at a slightly different aspect. This is now it's the absorption spectrum of, I think this is hydrogen, but anyway. If it's at rest, if the source of the spectrum is at rest. But they found that if the source is moving away from us, away from the spectroscope, that pattern, just as a unit, that all lines together, would shift towards longer wavelengths. It's called a redshift. That red has longer wavelengths than blue. They're moving away from us. Conversely, and by the way, the shift is proportional to the velocity that it's going. Blue shift means it's moving towards us. Same deal. So you could look at the heavens and not only see what something was made of, you could figure out how fast it was moving, at least along the line of sight. All right. So, it wasn't Herbert Curtis who found this. It was this uncomfortable-looking fellow named Festo Slipper. He was a Indiana farm boy, and when he became an astronomer, he joined the Lowell Observatory in 1901. Lowell Observatory was founded by this wealthy Bostonian person, Lowell, who is this gentleman here. And Lowell Observatory is perched on a clifftop, hilltop above Flagstaff, Arizona. And where you get really dark skies. The lady, by the way, is, I forget her name, but she was Lowell's assistant and probably did a lot of the observing herself. But of course, in those days, she didn't get credit for it. And here's our boy, Festo. Again, looking uncomfortable for the camera. Here is a much more characteristic and comfortable pose for him. In the 1910s, he used a new and very, very powerful and accurate spectrometer, spectroscope that was attached to the telescope. The telescope is up here, and it's down there. That's how astronomers actually work, by the way. They never look through their telescopes. They have instruments hooked to the back. But what he found is actually New Year's Eve, 1912 going into 13. He looked at Andromeda, for the first time got a spectrum of Andromeda. It's really hard to do the spiral nebula because they're faint and diffuse, and we couldn't get enough light to get a decent spectrum, but he managed it. And he discovered that Andromeda is blue shifted. It's moving towards us at 300 kilometers per second. That's, by the way, that's more than 300 times faster than a light report.
And what?
than a rifle bullet. Rifle bullet is not quite a kilometer a second. And it's also, by the way, 3 times faster than any known astronomical object. The stars are zipping around too, but not that fast. But okay, well, that was weird. By 1914, though, he had collected data for 15 spirals and found out that Andromeda was an anomaly. Almost all the others were redshifted. They're moving away from us, even faster. In 1921, they find one moving at 2,000 kilometers per second. And what? Again, what? Didn't know what it meant, but he did get a standing ovation at the American Astronomical Society. And in 1915, he determined by looking at the variation of redshift from one side of the nebula to another, that they're all rotating like pinwheels, which is sort of what you'd think, but it's nice to have evidence. But anyway, these numbers, these ridiculously high velocities, put Slipher, and this was part of the evidence that Curtis raised in the Great Debate. How could these things be part of the Milky Way? If moving at that velocity, they would have flown away a long time ago. They couldn't be part of the Milky Way. But okay, the Great Debate was a draw because, these were, neither side could offer anything more than plausibility arguments. The only way you could settle this was for somebody to go out and actually measure freaking distance to one of those nebulae. And it didn't have to wait long. This is how you get your name on a space telescope. Edwin Hubble, in 1924, when he was 35 years old, Hubble, like Shapley, was from Missouri. He wasn't from a farm like Shapley, but his father was an insurance executive. He was the golden boy in high school and college. He, handsome, easygoing, incredibly graceful and athletic. Captain every team. Fortunately for science, he became an astronomer. And in 1919, he joined the Wilson Observatory, which is perched over Pasadena, California, run by Caltech. And they had just inaugurated what was then the biggest telescope in the world. There's a mirror down here that does all the focusing and the collecting of light, and that's about 100 inches across, which is 3 yards. Here in that table. It's the biggest in the world, and best. He used that to look at Andromeda, and this is actually it's a positive plate he worked on. These are his notations, and he looked up there and found Cepheids in Andromeda. Now, that was a big deal because A, it's made of stars, not gas. And B, he was able to use the Cepheids to figure out how far away it was. And he got a number that was almost 1 million light years away. In fact, that's actually a pretty large underestimate. The modern figure is 2.5 million light years, and which means the light that we're seeing right there, the light that left Andromeda that we're seeing now, left there about a little before a creature called Homo habilis started walking around in Africa. That's how far away it is. But 1 million, 2.5 million, doesn't matter. It's a heck of a lot further away than anything Harlow Shapley had seen in our galaxy, in the Milky Way. So it had to be outside the Milky Way. So, bang, that settled the result, the debate right there. It's made of stars, it's way outside our galaxy. And Shapley, to his credit, accepted this almost instantly. He hated it, but he accepted it. By the way, it was about this time, actually it was 25, a Swedish scientist, now that it was clear the implications of Leavitt's work, nominated her for the Nobel Prize. Unfortunately, the Nobel Prize is not awarded posthumously. She deserved it, but in 1921, when Shapley took over as head of the observatory, he promoted her, raised her salary, and many of the other Harvard computers. But she was already dying of stomach cancer. She passed away that year, 1921. So there you have it. But in any case, Hubble didn't end there. He kept collecting Cepheid data from other galaxies. He and his assistant Milton Humason. In 1929, when he had data from a couple of dozen, he decided, not clear why, but he decided to plot the distances he was getting versus the redshift data that Besto Slipher had been getting. That's modern cloud data. That is probably one of the most famous scatter plots in the history of astronomy, or of science, because as you can see, and he drew a line, but there's a clear trend there. A lot of scatter, but the further out you go, the faster the redshift. A few are below zero, Andromeda is one of these down here. But most of them are redshifting, they're moving away from us. And there's this clear trend. Now, he kept going. That was, and he and Humason in 1931 published that. The original data are these red dots down here. He was getting distances out to something over 100 million light years, as we call it now, and velocities approaching 20,000 kilometers a second, 20,000 times faster than a light bulb. That is clearly a straight line. And you would think, considering this is one of the most epical discoveries in modern science, it would have caused a big stir at the time. But the basic reaction, including from Hubble, by the way, what did that even mean? It wasn't clear. I mean, didn't leap out at you. It wasn't a Eureka moment. In fact, one of the very few people to understand what it meant is shown in this picture. It wasn't the gentleman on the right, who I'm sure you all recognize. And it wasn't the distinguished looking fellow on the left, that was Robert Millikan, who was president of Caltech at the time this picture was taken in 1933. No, it was the shy looking priest. In the middle, Georges Lemaitre. He was a Belgian priest. He taught at the University of Louvain, but because he had a PhD in physics and had done graduate work in astronomy, actually I think he got his PhD in astronomy from Cambridge, he was teaching physics. In 1927, Lemaitre had taken Einstein's equations of general relativity. We don't have to go into that. But suffice it to say, it relates gravity to the shape to the curvature of space and time. But that's a whole other lecture. And he had applied those equations to the entire universe. What does that tell us he solved those equations. What is the shape of the universe? And what he discovered was that it's effectively impossible to have a universe that's just static or eternal. It pretty much, the physics turns out to be pretty much the same reason I can't just release these keys and have them hang there. It's either got to be going up or down. Well, there's a point where it comes around, and when you translate that to cosmic terms, it means the universe either has to be expanding or contracting. It can't just sit there. There's nothing to hold it there. And what he also realized, this was actually a footnote in his 27 paper, is that if you're anywhere you are in the universe, and say an expanding universe, just say it's expanding, you could look out at the other galaxies and you'd see them rushing away from you with a speed proportional to distance. Now, how does that even make sense? Imagine you have a bunch of ants standing on a ruler. And the ants are just standing still on the ruler, so far as they're concerned. They're not walking up and down the ruler, but you're stretching the ruler at a constant rate. It's a proper ruler. The ants, each ant thinks it's not moving, but it sees the other ants moving away from it because they're moving apart. And if you work it out, you realize that the speed at which the other ant's moving is proportional to the distance. And it doesn't matter which ant you start with. This guy thinks he's at rest and the other's moving that way. It's the same. There's nobody's at the center. You translate that to 3 dimensions, it's equivalent to taking a loaf of raisin bread with raisins embedded in it, and you're blowing up the loaf. And you look out in every direction, and you pick up a raisin, and it looks at the other raisins, and it sees them. The raisins aren't moving through that bread. The bread is expanding and carrying them along. And that was, galaxies aren't rushing away from us through space. Each one thinks it's at rest. Space itself is expanding and carrying galaxies along with it. That's what Lemaitre said. Now, unfortunately, few people realized that at the time Hubble published, because Lemaitre had published this paper in French in an obscure Belgian journal that nobody read. He didn't really get discovered until 31, which is another interesting story. And you think, okay, well, eureka, though. I mean, once people finally figured that out, well, clear, the universe is expanding. Must have started from something. You would think that the universe is expanding now, that it must have been much smaller in the past, right? If you extrapolate back to 0, then the universe must have had a beginning, right? Well, it turns out, even though they knew that the galaxies are rushing away, not even Hubble accepted the idea of a beginning. From Einstein on down, most astronomers hated the idea. They didn't even want to deal with the idea of the beginning of the cosmos. It's not something they could observe and study. It's unscientific. There may have been a bit of a reaction against anything spirogenesis, and who knows. Most of them didn't want to think about it. And in fact, there was so much resistance. This is what really surprised me when I noticed it, that the idea of the Big Bang had to be rediscovered 3 times before it finally took hold. And that's what we're going to talk about next week. Okay, well, I'm sure you're all sort of blitzed by that. Any questions? Yeah.
I once read something about Helen.
I'm sorry?
I once read something about Helen Swan Levitt.
Yeah.
And it said there was something, she implied something things that the universe is expanding, or that
I'm sorry, your master's novel.
I read about Helen Swan Levitt, and there was something in her writing that indicated that the universe was expanding. Is that right, or am I misinterpreting?
I'm not
That she
familiar
just
with
said.
Can you repeat the question, please?
That there was, question was whether there was something in Henrietta Leavitt's writings that indicated the universe was expanding. I don't know. I'm not familiar with that.
Maybe I misinterpreted.
It would have been very surprising, and I'm sure it would have been.
There was
more than that.
it's just that she indicated that distance could be determined.
Yeah, she, in her paper, I didn't go into this, but because the small Magellanic Cloud is way outside the distance you could get from parallax, you knew that, you know, she could get sort of the relative brightness was proportional to the period, but nobody knew exactly how bright those things were. To do that, and she does have this in her paper, she basically expressed the hope that astronomers would go out and look at Cepheids where you could get parallax and calibrate this, which of course they did almost immediately, one of them being Harlow Shapley. She didn't make a big deal of that discovery in her paper. But I don't know of anything she indicated about an expanding universe. Yeah. Anyone else? Yeah.
The observatory next door, is it still taking tours?
I'm sorry, say again?
The observatory?
Oh, the Naval Observatory?
No, no.
Yeah.
Is it open?
I believe they do run tours, at least they used to.
Yeah.
Run tours of the observatory itself. Remember, the vice president lives there, and, as well as a number of Navy admirals. But they do have tours of the observatory. It was established in the 1880s or so, somewhere in there. And it was originally, their telescope was designed to give a very precise measurement on certain stars when exactly overhead, and you could calibrate all the clocks in the country to that. Well, they use much more advanced methods, but they're still the official place that keeps time accurate to a whole bunch of decimal places these days.
Can you just talk for just a second about the latest telescope that I haven't read a lot about it, but I know that there's a telescope now that's just extraordinary.
Oh, the James Webb Space Telescope?
Must be.
Yeah. Well, as I said, Hubble got a telescope named after him, the Hubble Space Telescope, which was launched in 1990, and it has just been revolutionary. And it really has. I mean, that's not just hype. Excuse me. But the Hubble telescope was designed to take images of visible light and ultraviolet light. And of course, it's relatively small. It actually wasn't even quite as big as that 100-inch. It isn't even quite as big as that 100-inch telescope at Mount Wilson. There was a limit to how big a telescope you could put in a shuttle. That's what it came down to. And also, you've got this mirror, and you've got to keep it very, very rigid. Stars get very hard if you make it too big. But the one that was launched a year or two ago, the James Webb Space Telescope, that was the successor to Hubble. And it's been in development for like decades. It's been enormously successful after a very troubled development, by the way. Congress almost killed it several times. But they worked out all the problems, and they solved the size of the mirror problem, as you may have seen in the news. It was launched folded up. It's built as a series of hexagons, the mirror is. And so the whole thing was folded up to fit inside the rocket there. And then when it got out to where it was going, they unfolded it. Which, was like several heart-stopping weeks of, because if any piece of it had failed to lock into place, you wouldn't have had a telescope. So, but it worked. And the thing about the Webb telescope is that it's designed to see infrared light. That is longer than red. It's heat radiation, essentially, and even longer than that. And the beautiful thing about that is, well, two things. It's much bigger than Hubble, so it gets sharper images. That counts for those beautiful images you see coming back. But just as importantly, the detectors are sensitive to infrared heat radiation. And the beautiful thing about that for astronomy is, remember I talked about clouds of gas and dust? Well, it turns out that the Milky Way is a spiral. And that interstellar gas and dust is every freaking where out there. And it blocks our view. We actually, in visible light, we actually cannot see the center of the galaxy. We can see it in radio waves, and you can see it in infrared, because infrared actually can pretty well go through those gas clouds. It's just how it works. And so you're able to see not just the center of the galaxy, but look at all sorts of things, clouds, far distant galaxies, and you're seeing infrared light. And it turns out you can just learn an enormous amount that way. Now, to do that, I don't know if they have to have this very elaborate series of mylar sheets that are the size of tennis courts to shield the mirror from the sun. That thing can't ever point anywhere close to the sun, anywhere in the sky. And they're shielding it from the sun, and they're cooling it down to nearly absolute zero. It's like negative, I forget the exact figure, but it's like, it's like negative 400 degrees Fahrenheit. I mean, it's just about as cold as you can get. And that's so that the infrared radiation from the telescope itself doesn't wash out the images. I mean, it's very, very difficult to do. But, they did it, and it's just returning amazing science. That's the Webb telescope. But there are a bunch of telescopes. I mean, there are ground-based telescopes going online. One they named after an astronomer I'll talk about next week, Vera Rubin, just coming online in South America. There are lots of them. Yeah.
Thank you very much.
Yeah, thank you.
Is there a successor being planned to the Webb telescope?
There are ideas. I don't think anything's official yet. But yeah, you would still do the unfolding business because you got to launch it. But they figured that out by now. Actually, by the way, the Webb isn't the first mirror to be made of hexagons. That was a telescope that's in Hawaii. It's called the Keck telescope because it was funded by Mr. Keck. And it's made of hexagons. Anyway. Anybody else?
One last question.
Yeah, okay.
Could you define light year?
Yeah, sorry, I slipped that in. Well, we could have given, you could use, miles or inches or whatever you want to measure distances to stars. But you get really big numbers. And you know, even for astronomers, all those zeros, and you lose track. So there's a unit called a light year, which is how far a beam of light will travel in a year. Now, light's very fast. It's 186,000 miles per second. It takes about 8 minutes to get from the sun to the Earth. But anyway, 186,000 miles per second. If you had a beam, you know, circling the Earth, it could circle at about, it's 5 or 7 times per second. It's going all the way around the Earth, which gives you an idea. So that's really fast. And you say, well, let it go for a year. That's 1 light year. The nearest star is actually in the southern hemisphere. It's called Alpha Centauri. Is 4.6 light years. And there are other units that astronomers use, something called a parsec, but I'm not even going to try to explain that. It's a little over 3 light years. It's related to parallax. You know, light year is a common one. You know, so, but I said, but it makes it easy. So, you know, I say that Andromeda is 2.5 million light years away. I know that the light from it has taken 2.5 million years to get here.
In miles, a light year is 6 billion miles.
Yeah, right. And you know, there are no stars that close, so you have a lot of zeros.
A lot of zeros.